Hello guys, in this video we're going to look at how to solve problems regarding to acidic buffer solution by using an equation that is called the Henderson-Hasselbalch equation. We do know that to find the pH value for acidic solution, for a non-buffer solution that is acidic, we're going to use the formula pH equals to negative log times the concentration of H plus. However, when it comes to buffer solution, we're going to be using the Henderson-Hasselbach equation for acidic buffer solution. The formula will be looking like this. The pH is equals to the pKa plus log times the concentration of the conjugate base over the concentration of the weak acid. The reason why we're going to be involving Ka value now is because, remember, inside your buffer solution, we are involving weak acid, okay? And that's the reason why we're going to have the Ka value to be involved. Do remember that the concentration of conjugate base is the same as the concentration of the weak acid salts. So to find the concentration of conjugate base, you can simply get it from the concentration of the given weak acid salts. Let's have a look at the first example. In this question, it wants you to find the pH of the buffer solution. So given to you in the question are informations about a buffer solution. And the question wants you to find the pH of the buffer solution. Therefore, every single time when you see this pH of a buffer solution, this is what the question wants. Automatically, you should recall the Henderson-Hasselbalch equation. So to get the pH, we have to use the formula Henderson-Hasselbalch equation. We have the Ka value that is given to us right here. And we have more information given. We have the mass of the salts. Okay. So the question gives quite a few things. The question gives, number one, we have the Ka value, which is 1.8 times 10 to the power of negative 5. And we have the mass of the salts. Remember, this is your salts. So second, we have mass of CH3COONA, which is 0.8203 grams. Now, from the mass of salts given here, we can work out the number of mole of these salts, and thus we can also find the number of mole of the conjugate base. Remember, the concentration of conjugate base will be the same as the concentration of the weak acid salts. Therefore, the number of mole of the weak acid salts will be the same as the number of mole of the conjugate base. That is the mass of the salts. So we're going to work out the number of mole of salts by using this information later on. But before we're going to do that, let's find out any information given other than those two things right here. Given to you the volume and the molarity of the aqueous solution of your weak acid. So you have that one. Okay, so that is your weak acid. Thirdly, we have the molarity. CH3COOH aqueous equals to 0.10 mole per decimeter cubic, and the volume of the weak acid is 250 centimeter cubic. Do remember that we need to use Henderson-Hasselbalch equation. So we need to use pH equals to pKa plus log. So we're going to have the CH3COO minus and CH3COOH concentration, because this is the weak acid given to you, and therefore the conjugate base for your weak acid will be looking like this. Now, the concentration of this is given to you right there. Okay, the molarity is given to you already. And you have mass of your salts right there. So we want to find out what is the number of mole of this. So we're going to change this to number of mole, and we can get the concentration of your conjugate base. But before that, if you look carefully at this situation now, what we have now is you have your weak acid in aqueous form. So this is in aqueous form, and the question says that by dissolving. Okay, so what you have is you're gonna add solid salts. So we have 0.8203 grams of the salts. Now, when this solids is dissolved in your aqueous solution over here, therefore your buffer, okay, so this buffer solution, the volume will be 250 centimeter cubic as well. Okay, because we're going to be following the the volume of the weak acids that we have here, because you are dissolving solid salts inside there. If you have this in aqueous form, therefore the buffer volume will be the summation of both volume. So you have to bear that in mind. Okay, so in this situation now, you have an aqueous weak acid plus with the solid of your salts mixing together. And now your buffer volume will be 250 centimeter cubic as well. Right, now, next what we're going to be thinking about is how we want to think about getting the number of mole from there. Okay, we want to find the mole. Now, we want to find the number of mole of CH3COONA (0.8203). And to change this to mole, we have to divide this with the molar mass of CH3COONA, which is about 82.03 gram per mole. So after you have done that, the number of mole for CH3COONA would be about, so the number of mole would be about 0.01 mole. Okay, now this is very important for you to remember. Just now we have told you that the mole of CH3COONA will be the same as mole of CH3COO-. Why? Because when you dissolve CH3COONA in aqueous, it will be fully dissociated to form CH3COO-. Okay? Fully dissociated plus Na. So when you look at this equation, 1 mole of CH3COONA will be producing 1 mole of your conjugate base. So if you can find the number of mole of your salts, you can also find the number of mole of your conjugate base. Now, therefore, mole of CH3COO- is 0.01 mole. Okay, so by doing this, you will be able to get this one mark. Okay, you get 1 mark right here. You get 1 mark right there. Now, we have figured out the number of mole of your conjugate base, but what about the molarity? Because we need to plug in the molarity value over here. Therefore, next, we need to find the molarity of CH3COO- aqueous. We have found that (0.01) mole of CH3COO minus provided just now from the step over here. So to change this into molarity, we're going to use the formula molarity equals to mole over liter. Okay, we have the mole right here. Okay, we have mole right there, so we can plug that into here. Now, what about your volume? What is the volume that we need to use? Remember from the visualization that we have done from the question, a buffer solution is prepared by dissolving. So we are dissolving the salts into your weak acid. And then your weak acids, the volume is 250 centimeter cubic. And this is going to be the volume for the buffer as well. And automatically, this will be the volume for your CH3COO minus. So the liter over here the volume will be 250 centimeter cubic, and we're going to change that to liter. So we have 0.25 decimeter cubic. So that is the volume that we're going to put into there to find the molarity of your CH3COO minus conjugate base. Therefore, the molarity of CH3COO minus is 0.01 mole over 0.25 decimeter cubic, and we have about 0.04 mole per. I'm going to write that again. So the molarity is 0.04 mole per decimeter cubic. So this is the molarity of your conjugate base. So by using this formula, you have 1 mark. By writing that molarity, you get another 1 mark. So what we need to do now, we're just going to plug in that value into your Henderson-Hasselbalch equation right here to find the pH of the buffer solution. Okay. So we're just gonna plug in the molarity value into the equation. So we're just going to plug in the value of molarity into the equation. The Henderson-Hasselbach is pH equals to P Ka plus log concentration of your conjugate base over concentration of the weak acid. Ka value is given. So the Ka value, if you go back to your question, the Ka value is right here. So we're just going to plug in the value into there. We have the concentration already given to you of the weak base, which is 0.1. So we're just going to plug in that into there. So pH equals to P right here, guys. This P is equals to negative log, okay? That P right there is equals to negative log. So you have 1.8 times 10 to the power of negative 5 plus log. We have 0.04 mole per decimeter cubic and 0.10 mole per decimeter cubic. By putting all the value inside, you're just gonna punch a calculator and you should be getting a value like this. By using this formula, you get 1 mark. By getting the right answer, you get another 1 mark. So this is how you're going to find the pH of a buffer solution by using the Henderson-Hasselbach equation. Now that's quite easy. The only challenge is for you to visualize this. You need to know what is the volume of the buffer solution and what is the volume of the conjugate base. This is the only higher order thinking part of this question. The rest of it is quite easy. But the difficult part is when we have situation like this. It's the same question, same salts, same value of salts, okay? We have the same volume, we have the same molarity of your weak acids, but you need to calculate the pH of the buffer after the addition of a small amount of strong acid. So the step is going to be a little bit more complicated than what we have done just now. Yes, we're still going to be using the Henderson-Hasselbach, but before we would be able to do that, we have to do a few more steps. Now, always remember to highlight what the question wants. So that is what the question wants. We want to find the pH of the buffer. So we're going to be using the Henderson-Hasselbach equation, but this time we have the addition of small amount strong acid. Okay, so we gonna be using the same pH equals to pKa plus log concentration of CH3COO minus. Okay, it's still the same Henderson-Hasselbach, but now we have a small amount of strong acid is added. So imagine you have this is your weak acid. Okay, so the weak acid is how much? You have 250 centimeter cubic. Molarity is given. So this one is about 250 centimeter cubic. and we're gonna add with solid of salts. Okay, so the salts is this, that is the salts. Then we will be producing a buffer. So we have your buffer here. The volume is 250 centimeter cubic. Why? Because this one is in solid form. This one is in aqueous form. And we're going to have the buffer solution to have the same volume as your weak acid. So it's common sense. So when you have your something that is in aqueous with a volume and you try to dissolve some solids, the volume doesn't change. Okay, so it will be the same for the buffer right here. Now the situation now, we have the addition of HCl this much. So we're gonna take some HCl, about 1.0 centimeter cubic, just a little bit of HCl with the molarity of 1 mole per decimeter cubic. So we're gonna add into your buffer solution. And now what is the pH? So that is the situation. To start, we're gonna find out the number of mole for the conjugate base and for the weak acid before adding the small amount of hydrochloric acids, your strong acids, into the buffer solution. Question gives mass of the salts is this. Okay, so we have that mass of salts. Since salts is fully dissociated, like what we have discussed just now, the number of mole of CH3COO minus, which is that, the one that we want to find, will be the same as the salts CH3COO and A. So we're just gonna zero point 8 to 0.3 grams. Okay, so from mass, you're gonna change back into mole. So you're gonna divide by the molar mass, 80.23 gram per mole. So this is the molar mass for your salts. Okay, so I'm going to highlight that. That is the molar mass for this. Okay. And we will get 0.01 mole. By finding that number of mole, you get 1 mark. And for the weak acid right here, question gives the concentration, which is CH3COOH. The concentration given to us 0.10 mole per decimeter cubic, and the volume of the weak acids is about 0.25 decimeter cubic. To find molarity, to find mole, we're going to use the molarity given to you right here, and we're going to be multiplying with the volume. And we get 0.10 mole decimeter cubic times with 0.25 decimeter cubic, and we should be getting 0.025 mole. By figuring out the number of mole of CH3COOH before adding HCl, you'll be getting another 1 mark. Okay. Next, the question is how much hydrochloric acid is added, even though it's a very small amount, but we need to know how much of that being added, because later on we're going to put that information to a table that resembles the ICE table, but it's going to be a bit different. The question gives the concentration of HCl 1.0 mole per decimeter cubic and the volume of hydrochloric acid added into your buffer 1.0 centimeter cubic. Bear in mind that all of this is added into the buffer. Remember that concentration of HCl will be the same as the concentration of H+. The reason is because strong acid will be fully dissociated in aqueous solution. So we need to find the number of mole. What is the mole of H+ added? So this is the most important thing we need to find now. To find mole, it's quite easy. We have the molarity. Okay, we're going to have the molarity times with volume. And the molarity is 1.0 mole decimeter cubic, and we're going to times with 1.0 over 1000 because we have to change that to decimeter cubic. And the mole of H+ would be 1 times 10 to the power of -3 mole of H+. So that is the how much H+ is added into the buffer. By finding this, you'll get another 1 mark. We're going to take all of this mole, number of mole right here, number of mole for conjugate base, number of mole for your weak acids, and also the number of mole of the added HCl, and we will be putting that into a table that is called the IACF table. The function of this table is different from the ICE table. The ICE table is for us to use that one to find the information about something at equilibrium, but this one, we're going to use this to find the final mole after you have added the strong acids into the buffer or strong base into the buffer solution. Remember, for buffer solution, if you want to find out what is the pH after the addition of strong acids or strong base, we're going to use the IACF table. The initial mole of CH3COO-, we have that already. So the initial mole is right here. We have all the initial mole. And this is what we have added inside. We're just going to plug in the value into the IACF table. So initial, the value at initial, we have 0.01. Remember, it will be in terms of mole. Okay, we're going to be working in terms of mole for IACF. We don't have this in the beginning. Okay, we don't have that. And we have this 0.025. If you go back to the page over here, so that is the initial mole of weak acid before you add hydrochloric acid. So all of these are the values initial. And of course, this one, you don't have the addition, but we have the addition of H plus. Remember, this H plus over here comes from the strong acid. And how much do we add? We have 1.0 times 10 to the power of -3. So this much. It's a very small amount of strong acid. Remember, the H plus right there. This is from the HCl. I'm going to do that again. That one is from the HCl added. Okay. So this is the addition. So when you add this, you're going to minus that in change here, and you're going to minus that one in there. But you're going to add for this one, because this is the product side. When you have CH3COO- combining with this, you will be producing your CH3COOH. We're going to be using the non-reversible arrow for simplicity, in this case, for IACF. So over here for the change, we're going to be minus, because this one will be used up. Okay. And this one also minus 1.0 times 10 to the power of -3. So we use minus because they will be used up. This is the forward reaction. They will be used up. And over this side, you will be adding 1.0 times 10 to the power of -3. So final mole is 0.01 minus this number. You should be getting a number about 9 times 9.0 times 10 to the power of -3. This one will be 0 because you have 1 times 10 to the power of -3 minus with 1 times 10 to the power of -3, whereas this one 0.025 plus 1 times 10 to the power of -3, then you get 0.026. So this is the most important part of the we have found out the final mole for CH3COO minus and final mole for CH3COOH. And we are nearly there to plug that into the Henderson-Hasselbach equation. We take the final mole of these species and we have to work out the final molarity. So the final molarity is, mole final is this just now. And remember the volume okay, so the volume now is the volume of buffer plus HCl. The buffer you have is 250 and the HCl is about 1.0 just now. Yes? So the volume will be 251.251 centimeter cubic. So this is the new volume. By getting the new volume, you will get another 1 mark. By the way, you'll get 1 mark right here. You get 1 mark right there. And all the way there. Also, you will be getting 1 mark for this equation you're going to be writing on top. Okay, let's continue with this. We have the new volume right now because you have the aqueous buffer solution plus with the aqueous HCl. So of course you're going to have a new volume and we're going to divide this with this to get the molarity. And now the molarity of CH3COO minus final is 9.0 times 10 to the power of negative 3 over 0.251 decimeter cubic. And the molarity is about 0.036 mole decimeter cubic. So this is the molarity. And by getting the final molarity for this, you get 1 mark. For the weak acids, the mole final is 0.026 mole. The volume also the same. You're going to have the buffer, which is 250 centimeter cubic, plus with the HCl 1.0 centimeter cubic, and the volume is about 251.0 centimeter cubic. That is the new volume. You've got the mark over here already, so it should be the same as that one. So we can proceed to find out the final molarity concentration for weak acids, and that should be 0.026 mole over 0.251 decimeter cubic, and the molarity is 0.104 mole decimeter cubic. You have 1 mark right there. So we're going to take we're going to take this and we're going to take this value and we're just going to plug into your Henderson-Hasselbalch equation. Okay? So the pH is equals to negative log 1.8 times 10 to the power of negative 5 plus log, so the concentration is 0.036 and 0.104. So the pH is 4.28. So that is the pH after you have added a small amount of strong base. So you get 1 mark for this, 1 mark for the Henderson-Hasselbalch equation. Okay, so remember the concentration. This is the final concentration. You get here 0.036, 0.036, and the concentration for this at final 0.104, 0.104, and you get this 4.28. So when you compare with the pH of the buffer, it's only a very small change. This is the pH when you don't add a small amount of strong acid. And when you look at after you have added a small amount of strong acids, the change is pretty small. It's about 4.28. The third one is when we have the same buffer solution. As you can see, it's still the same buffer solution, but this time we need to find the pH value of the buffer after we are adding small amounts of strong base inside. In the second example that we have looked just now, we have added a small amount of strong acid. This time, we're going to look for the pH value of the buffer solution. So what is the new pH value for the buffer solution when we introduce a small amount of strong base? The question wants to find the pH of the buffer. So we're going to use Henderson-Hasselbalch, but before we're going to go to that part, there are a few steps that we need to do before we can reach to the Henderson-Hasselbalch equation, just like what we have done for the addition of small amount of acid. This time, the addition of this much of sodium hydroxide. Question gives the buffer solution. You dissolve the solid salts in the aqueous solution of weak acid. So the situation will be the same. Okay. So we have this is the weak acid, 250 ml, and you add with the salts 0.8203 grams. So when you add those two together, you'll get a buffer. So now you have your buffer solution. The volume is 250 centimeter cubic. And what happened? We're going to add a small amount of strong base. Okay, so we have, this is the strong base. So we're going to add a small amount in there. How much? It's going to be 1.0 centimeter cubic and 1.0 mole per decimeter cubic. So this is the volume that we are adding inside your buffer. So now you can imagine that we adding strong base, small amounts with this concentration, 1.0 mole per decimeter cubic. That much, 1 centimeter cubic, we're gonna add into your buffer. So we need to think about what is the pH now after that. Okay. So we need to find the number of mole. We have done this just now for the addition of strong acid. So it will be the same because we are still using the same buffer solution. So you get the number of mole of your CH3COO minus and the number of mole of your weak acid. Remember, this is the molar mass of your salts. Okay, still gonna get 1 mark right here. You're gonna get 1 mark right there for getting the number of mole. And how much sodium hydroxide is added? Question tells you that the concentration of sodium hydroxide is 1.0 mole per decimeter cubic and the volume added 1.0 centimeter cubic. Okay, bear in mind, this is the information of how much sodium hydroxide is added into the buffer. Okay, this is how much added into the buffer. Remember that. Now, to find the number of mole of sodium hydroxide added, we need to also remember the concept of strong base will be completely dissociated. So when you have complete dissociation, the number of mole of your base will be the number of mole of your OH minus. Okay? So when you get the number of mole of your OH minus, you can use that in your IACF table. Right. So we want to find mole of OH minus. So how do we do that? We're going to take the molarity, 1.0 mole decimeter cubic times with 1.0 over 1000 decimeter cube. Okay, because we need to change this. This is centimeter cubic, so we have to change it. Therefore, mole of OH minus is about 1 times 10 to the power of negative 3 mole. So we get another 1 mark right there. We take all of these information again, like what we have done for the strong acid addition. We're going to write that into the IACF table to find out the final mole. And from the final mole, we can work out the final molarity. So the initial is CH3COOH is 0.025. Okay, so if you go back here, CH3COOH will be 0.025. Remember, this is the one that will be So we take the final mole that we have got from the table just now, and we're going to work out the final concentration. The final mole for CH3COO minus is 0.011, and the volume, remember, it will be buffer plus NaOH added. Buffer is about 250, NaOH is 1, therefore the volume is 251 centimeter cubic. So the concentration CH3COO minus final will be 0.011 over 0.251 decimeter cubic, and the molarity of that will be 0.044 mole decimeter cubic. Okay, so you'll get 1 mark for the volume that you have worked out. Remember, it's the summation of both aqueous solution added together, and this also you get 1 mark. For the acid, mole final for the acid is 0.024, and the volume also buffer plus the NaOH, then you get 251 centimeter cubic. Okay, so the concentration final is 0.024 mole over 0.251 decimeter cubic, 0.096 mole decimeter per decimeter cubic. That is the final mole, and you get 1 mark over here. Okay, remember the volume is still going to be buffer plus the NaOH, then you get 251 centimeter cubic, and you change that into decimeter cubic when you want to find molarity. We take the value final, we're going to plug into the Henderson-Hasselbach equation. So pH is equals to, remember, P is negative log 1.8 times 10 to the power of negative 5 plus log, and you have 0.044, 0.096. So this is the concentration of conjugate base, 0.044, conjugate base, 0.044, and underneath is the concentration of your weak acid, okay, 0.096. Let's check. 0.096 for the conjugate. This is for the conjugate base, and this is for the weak acid, 0.096. You plug that into your Henderson-Hasselbach, and finally you'll get the pH value equals to 4.4. You get 1 mark for using the equation, 1 mark for the final answer.